Tonight, we're going to talk about something that shouldn't exist. A world so massive, so impossibly large, that it challenges everything we thought we knew about how planets form. When astronomers first discovered it, they had to double-check their calculations because the numbers didn't make sense. This isn't just a big planet. It's a giant beyond comprehension. And by the end of tonight, you're going to understand why finding planets this large changes our entire understanding of what's possible in the universe. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what you think a planet is. You probably picture something like Earth, a rocky world with a solid surface you could stand on. Or maybe you think of Jupiter, a massive ball of gas with swirling storms and colorful bands. Both are planets, but they're wildly different in almost every way. Earth is small and dense, with a surface made of rock and metal. Jupiter is huge and mostly hydrogen and helium, so light that it would float if you could find an ocean big enough to put it in. But there's a limit to how big a planet can get. At a certain point, when you add more and more mass, something fundamental changes. The object starts to compress under its own gravity. It starts to heat up internally. And eventually, if it gets massive enough, it crosses a threshold where it's no longer a planet at all. It becomes something else entirely. That threshold sits at about 13 times the mass of Jupiter. At that point, the pressure and temperature in the core become high enough to start fusing deuterium, a heavy form of hydrogen. When that happens, the object is classified as a brown dwarf, not a planet. Brown dwarfs are failed stars, objects that aren't massive enough to sustain full hydrogen fusion like our Sun does, but too massive to be considered planets. They exist in a strange middle ground between planets and stars. So there's a hard limit. Anything below 13 Jupiter masses is a planet. Anything above is a brown dwarf. Simple, right? Except it's not simple at all. Because we've found objects that blur this line in ways we never expected. Jupiter is the largest planet in our solar system. It measures about 86,881 miles, or about 139,820 kilometers across. That's more than 11 times wider than Earth. If Earth were the size of a grape, Jupiter would be a basketball. The volume difference is even greater. You could fit about 1,300 Earths inside Jupiter. And yet, Jupiter only contains about 318 times as much mass as Earth. Why the difference? Because Jupiter isn't dense. It's mostly hydrogen and helium, the lightest elements in the universe. Its average density is only about 1.33 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. Jupiter is just slightly denser than water. Now, here's something counterintuitive. If you kept adding mass to Jupiter, it wouldn't keep getting bigger. At a certain point, around 3 times Jupiter's mass, a gas giant planet reaches its maximum size. After that, adding more mass actually makes the planet smaller, not larger. The additional mass compresses the interior. The gravity becomes stronger. The hydrogen gets squeezed into denser and denser states. The planet shrinks even as it gains mass. This means Jupiter is close to the maximum size a planet can be. You can have planets with much more mass than Jupiter, but they won't be much bigger in diameter. In fact, they might be smaller. This is the mass versus size paradox that confuses most people when they first learn about it. More mass doesn't always mean more size, at least not for gas giant planets. In 2011, astronomers made a discovery that would reshape how we think about planetary mass. They found an object called Rox's 42Bb, and this thing is a monster. Rox's 42Bb has a mass roughly 9 times that of Jupiter. It's one of the most massive objects we've ever found that we still classify as a planet. The object orbits a young star in the Rho Ophiuchi star-forming region about 460 light-years from Earth. That's about 2,700 trillion miles away, or about 4,350 trillion kilometers. The light we're seeing from this system started its journey to Earth around the year 1564, when Galileo was born, and Shakespeare hadn't even been written yet. When I say young, I mean extraordinarily young by cosmic standards. The star is only about 2 million years old. Our Sun is 4.6 billion years old. This star system is still in its infancy, barely formed. The star is still surrounded by remnants of the cloud from which it formed. Gas and dust still swirl in the disk around it. The system is chaotic, unstable, still settling into whatever configuration it will eventually reach billions of years from now. And orbiting this young star at a distance of about 157 astronomical units is this massive planetary mass object. 157 astronomical units. That's 157 times the distance from Earth to the Sun. Let me put that into perspective with real numbers. Earth orbits at 1 astronomical unit, which is about 93 million miles, or 150 million kilometers. So Rox's 42Bb orbits at roughly 14.6 billion miles, or about 23.5 billion kilometers from its star. The Voyager 1 spacecraft, humanity's most distant probe, launched in 1977 and has been traveling for over 45 years. It's currently about 160 astronomical units from the Sun, just slightly beyond Rox's 42Bb's orbital distance. At that speed of 38,000 miles per hour, it took 45 years to reach that distance. If you wanted to send a spacecraft to visit Rox's 42Bb at its own star, the journey would take thousands of years. At that distance from its star, Rox's 42Bb receives almost no warmth from its parent star. The star appears as nothing more than a very bright point of light in the planet's sky, barely distinguishable from other stars, except for its brightness. The amount of energy the planet receives from its star is minuscule, probably less than 1/10,000th of what Earth receives from our Sun. At that distance, it takes roughly 2,000 years to complete one orbit around its star. The orbital velocity is extremely slow by planetary standards. The planet is moving at only about 0.6 miles per second, or about 1 kilometer per second, relative to its star. For comparison, Earth orbits at about 18.5 miles per second, or about 30 kilometers per second. Rox's 42Bb crawls through its orbit at a glacial pace. The object itself is absolutely massive. 9 Jupiter masses puts it right up against that boundary between planet and brown dwarf. Remember, 13 Jupiter masses is where we draw the line. Rox's 42Bb is just below that threshold. To understand the scale, Jupiter is about 318 times more massive than Earth. Rox's 42B is 9 times more massive than Jupiter. That means it's nearly 3,000 times more massive than Earth. And here's something that really puts the orbital distance in perspective. Earth takes 365 days to orbit the Sun once. 1 year. Rox's 42BB takes 2,000 years to complete a single orbit. While Earth has circled the Sun 2,000 times, Rox's 42BB completes just one lap around its star. But here's what makes it so remarkable. Despite having 9 times the mass of Jupiter, it's only about 1.1 to 1.4 times larger in diameter. Let me say that again, because it's counterintuitive and people often miss it. 9 times the mass, but only slightly bigger. Most people assume that if you have more mass, you automatically have more size. That works for solid objects. If you have a boulder and you add more rock to it, it gets bigger. If you have a building and you add more floors, it gets taller. But gas giants don't work that way. This is that compression effect in action, and it's one of the most fascinating aspects of planetary physics. Here's why it happens. When you have a ball of gas held together by gravity, the gas in the center is being squeezed by all the gas above it. The more gas you add, the more weight presses down on the core. At first, when you add more mass to a planet, it does get bigger. The additional mass adds volume. But as you keep adding mass, the gravity gets stronger and stronger. Eventually, the gravity becomes so strong that it compresses the interior gas more than the new mass expands the exterior. The planet stops getting bigger and actually starts getting smaller even as you add more mass. Jupiter is right around the sweet spot where a gas giant planet reaches maximum size. At about 1 to 3 Jupiter masses, a gas planet is as large as it can be. Add more mass, and the planet shrinks. The interior pressure increases. The hydrogen gets compressed into different phases. At normal conditions, hydrogen is a gas, molecules of 2 hydrogen atoms bonded together. But under extreme pressure, hydrogen stops behaving like a gas. First, it becomes a liquid, but not like water. It's a molecular liquid hydrogen, still made of H2 molecules, but in liquid form. This happens at pressures of millions of atmospheres. Then, at even higher pressures, the hydrogen molecules break apart. The atoms get so close together that their electrons can move freely between atoms. This is called metallic hydrogen because it conducts electricity like a metal. In this state, hydrogen is exceptionally dense, far denser than any terrestrial material. It's estimated to have a density around 0.6 to 0.8 grams per cubic centimeter at the pressures found in Jupiter's interior. Inside Rox's 42BB, with 9 times Jupiter's mass, the pressures are even more extreme. The core pressure is probably in the tens of millions of atmospheres. At those pressures, hydrogen is compressed into states we can barely study in laboratories. All that extra mass is squeezed into this extremely dense core. The planet doesn't expand outward much because the gravity is so strong, it holds everything in tight. The result is a world with 9 times the mass, but only slightly larger diameter. The average density is much higher than Jupiter's. Jupiter has an average density of about 1.33 grams per cubic centimeter. Rox's 42B probably has an average density somewhere around 4 to 6 grams per cubic centimeter, depending on its exact size. That's denser than many rocks. It's a gas giant with a density approaching that of solid materials. This seems paradoxical until you understand the physics of extreme compression. The interior of this planet is crushing itself under its own weight. The gravitational field at the cloud tops is probably 2 to 3 times stronger than Jupiter's. If you could somehow stand on a solid surface at the visible top of Rox's 42 BB's atmosphere, you'd weigh 2 to 3 times what you weigh on Jupiter. And on Jupiter, you'd already weigh about 2.5 times what you weigh on Earth. So, on Rox's 42 BB, you'd weigh 6 to 7 times your Earth weight if you could somehow survive there. Of course, you couldn't survive. There's no solid surface to stand on. You'd fall through the atmosphere, getting crushed and incinerated as you descended into the increasingly hot and dense interior. And the temperature? Rox's 42 BB has an estimated temperature of around 1,800 degrees Fahrenheit or 1,000 degrees Celsius. That's hot enough to melt most metals. Gold melts at 1,945 degrees Fahrenheit or 1,063 degrees Celsius. Silver melts at 1,763 degrees Fahrenheit or 962 degrees Celsius. Rox's 42b. B is just below these temperatures at its cloud tops, but the interior is far hotter. And here's what's remarkable about this heat. It's not coming from the star. The object is so far from its star that it receives almost no warmth from it. The star appears as little more than a bright point of light in the sky. The energy Rox's 42 BB receives from its star is negligible, probably less than 1 watt per square meter. For comparison, Earth receives about 1,368 watts per square meter from our Sun. So, where is this extreme heat coming from? It's internal heat, left over from the formation process. When a gas giant forms, the process releases tremendous amounts of energy. Gravitational potential energy gets converted into thermal energy. Think about what happens during formation. Gas from the protoplanetary disk falls onto the growing planet. As it falls, it accelerates, pulled by the planet's gravity. When it crashes into the planet's atmosphere, all that kinetic energy converts to heat. The more massive the planet, the more energy is released during formation. For a planet as large as Rox's 42 BB, the formation process would have been extremely energetic. The gravitational collapse would have heated the interior to tens of thousands of degrees. The planet would have been glowing, white-hot, visible across interstellar distances. Over time, this heat radiates away into space. The planet slowly cools. But for massive planets, this cooling process takes a very long time. The planet has enormous thermal mass. There's a huge amount of heat energy stored in the interior. And the heat has to make its way from the deep interior to the surface before it can radiate away. Heat transfer in the interior happens through convection. Hot material rises, cool material sinks, creating circulation patterns. But this process is slow, especially for such a massive object. Computer models suggest that a planet like Rox's 42 BB, with 9 Jupiter masses and only 2 million years old, it should have an internal temperature of perhaps 50,000 to 100,000 degrees Fahrenheit, or about 28,000 to 56,000 degrees Celsius, in the core. That's hotter than the surface of our Sun, which is about 10,000 degrees Fahrenheit, or 5,500 degrees Celsius. This internal heat drives powerful atmospheric dynamics. Winds in the upper atmosphere could reach hundreds or thousands of miles per hour. Storms larger than Earth could rage for centuries. The atmosphere is in constant turbulent motion, powered by the heat rising from below. The 1,800-degree Fahrenheit temperature we measure is just the cloud top temperature. The temperature at the level where the atmosphere becomes optically thick and we can't see deeper. Below that, temperatures rise rapidly. Descend 62 miles into the atmosphere, and you'd encounter temperatures of several thousand degrees. Descend 621 miles, and you'd be in a furnace, tens of thousands of degrees hot. The pressure would crush you long before the heat incinerated you. What's also fascinating is the planet's thermal evolution. Right now, at 2 million years old, it's still very hot. But it's cooling. Every year, it radiates a tiny bit more energy into space than it receives from its star. The deficit is made up by the internal heat reservoir. Slowly, over millions and billions of years, the planet will cool down. In 10 million years, the temperature might drop to 1,500 degrees Fahrenheit, or 815 degrees Celsius. In 100 million years, maybe 1,000 degrees Fahrenheit, or 540 degrees Celsius. In a billion years, perhaps 700 degrees Fahrenheit, or 370 degrees Celsius. The cooling isn't linear. It happens faster at first when the planet is hottest, then slows down as the temperature drops. Eventually, billions of years from now, Rox's 42BB will be a cold, dark world. The internal heat will have radiated away. The temperature will drop to just a few hundred degrees above absolute zero, barely warmer than the background temperature of space. The planet will no longer glow in the infrared. It will be invisible to most telescopes. But right now, we're seeing it in its infancy, still hot from formation, still radiating the energy released when it came together. A world in the process of cooling and settling into its final state. This thermal emission is what allowed astronomers to detect it in the first place. If Rox's 42BB were older and cooler, we probably wouldn't have found it yet. The fact that we can see it tells us something important. It's young. Now, you might be wondering, how do we even find something like this? How do you spot a planet 460 light-years away orbiting so far from its star? The answer is direct imaging, and it's one of the most technically challenging things astronomers do. Most exoplanets are found using indirect methods. We don't actually see the planet itself. We detect its effect on something we can see. The transit method watches for a star to dim slightly when a planet passes in front of it. Imagine staring at a spotlight 300 feet away. Now, someone walks in front of that spotlight carrying a small coin. The coin blocks a tiny fraction of the light. That's essentially what we're looking for with the transit method. Except the star is trillions of miles away, and the planet might block only 1% or less of the star's light. The radial velocity method looks for the wobble a planet's gravity causes in its star. As a planet orbits, both the planet and the star actually orbit their common center of mass. For a massive planet, this causes the star to wobble back and forth. From Earth, we see this wobble as a shift in the star's light. When the star moves toward us, its light shifts slightly toward the blue end of the spectrum due to the Doppler effect. When it moves away, the light shifts toward the red. These shifts are incredibly small. For a Jupiter-mass planet orbiting a Sun-like star, the velocity change is only about 27 miles per hour. And we have to detect this by analyzing light from a star trillions of miles away. It requires extremely precise spectrographs and careful analysis. But Roxy's 42BB was found by actually taking a picture of it. Not an artist's illustration. Not a diagram. An actual photograph showing both the star and the planet as separate points of light. This is incredibly difficult for several reasons. First, stars are incomprehensibly brighter than the planets that orbit them. Our Sun is about 1 billion times brighter than Jupiter. Trying to see a planet next to a star is like trying to spot a firefly hovering next to a lighthouse beam while standing 10 miles away. The planet's light is completely overwhelmed by the star's glare. Second, most planets orbit close enough to their stars that even our best telescopes can't separate them. The angular separation is too small. It's not that the planet is physically small, it's that the angle is tiny as seen from Earth. Imagine trying to distinguish two headlights on a car that's 50 miles away. Even though the headlights are 3 feet apart on the car, from 50 miles away, they look like one light. Your eye can't resolve them as separate. The same problem affects telescopes trying to image planets. But Roxy's 42BB has some advantages that make it easier to image. First, it's very far from its star. 157 astronomical units of separation. From Earth's perspective, 460 light-years away, that translates to an angular separation of about 1.1 arcseconds. An arcsecond is 1/3600th of a degree. To put that in perspective, the full moon in the sky is about 1,800 arcseconds across. So, Roxy's 42BB appears separated from its star by about 1/1600th of a full moon's width. That might sound impossibly small, but it's actually quite large by exoplanet standards. Many exoplanets have angular separations of only a few hundredths of an arcsecond. Those are essentially impossible to image directly with current technology. But 1.1 arcseconds is within reach of our best telescopes equipped with the right technology. Second, Roxy's 42BB is extremely hot for a planet. That means it's emitting a lot of infrared radiation that specialized telescopes can detect. In infrared light, the brightness ratio between star and planet is much more favorable than in visible light. The star is still brighter, but not by as much. Instead of being 1 billion times brighter, the star might only be 10,000 to 100,000 times brighter in the infrared. That's still a huge ratio, but it's manageable with the right techniques. Third, the star itself is young and relatively faint. Young stars are more active, but they're also not as bright as older, fully mature stars. This helps reduce the glare problem. To actually image Roxy's 42BB, astronomers used the Keck Observatory in Hawaii. Keck has 2 10-meter telescopes, among the largest optical telescopes on Earth. 10 meters is about 33 feet. The mirrors are massive, built from 36 hexagonal segments that fit together like a honeycomb. But a large mirror alone isn't enough. Earth's atmosphere is a major problem for ground-based astronomy. Turbulence in the atmosphere causes stars to twinkle. That twinkling looks pretty to the naked eye, but it's a disaster for high-resolution imaging. The atmospheric turbulence blurs images, smearing out fine details. Even with a perfect telescope, the atmosphere limits resolution to about 1 arcsecond at best. This is where adaptive optics comes in. Adaptive optics is a technology that corrects for atmospheric turbulence in real time. Here's how it works. The telescope observes a bright star near the target object. Light from this star passes through the same atmospheric turbulence as light from the target. A wavefront sensor analyzes how the turbulence distorts the starlight. Then, a deformable mirror in the telescope changes shape hundreds or thousands of times per second to counteract the distortion. The mirror literally flexes, compensating for the atmospheric turbulence. The result is an image almost as sharp as if the telescope were in space. With adaptive optics, the Keck telescope can achieve resolution of about 0.04 arcseconds, much better than the 1 arcsecond seeing limit. But even with adaptive optics, you still have to deal with the brightness problem. The star is still much brighter than the planet. To solve this, astronomers use a coronagraph. A coronagraph is a device that blocks out the star's light, creating an artificial eclipse. It's like putting your thumb over the sun to see the landscape around it. The coronagraph has a small opaque disk that blocks the star. The star's light is stopped, but light from objects near the star, like planets, can still reach the detector. This doesn't work perfectly. Some starlight still leaks around the coronagraph. And the bright star creates diffraction patterns, halos of light that spread out from the star's position. These have to be carefully subtracted in post-processing. Astronomers take multiple images, sometimes with the telescope rotated at different angles. They then use sophisticated algorithms to subtract the starlight and diffraction patterns, revealing the faint point of light that's the planet. It's a painstaking process, requiring lots of telescope, time, and computational analysis. But it works. The final image shows Rox's 42b as a distinct point of light separated from its star. But finding a point of light isn't enough. You have to prove it's actually orbiting the star, and not just a background star or galaxy that happens to be in the same line of sight. This requires multiple observations spread over years. If the object is truly orbiting, it will move relative to the star over time. Its position will change in a way consistent with orbital motion. Background objects, on the other hand, won't move or will move in a way inconsistent with being bound to the star. Astronomers observed Rox's 42b over several years. They measured its position relative to the star in each image. The measurements showed consistent motion along an orbital path. The object was moving exactly as expected for something gravitationally bound to the star. This confirmed it was indeed a planet, not a foreground or background object. The entire process, from initial detection to confirmation, took years of work. Multiple observing runs with the Keck telescope, hundreds of hours of telescope time, thousands of hours of data analysis, careful measurements and orbital fitting, peer review and publication. It's a massive, collaborative effort involving dozens of scientists and engineers. But the result is undeniable. A photograph of another world, 9 times more massive than Jupiter, orbiting a star 460 light-years away. Direct imaging is still limited to a small subset of exoplanets. The planets have to be massive, hot, young, and far from their stars. They have to orbit relatively nearby stars, so the angular separation is large enough to resolve. Most exoplanets don't meet these criteria. But for the ones that do, direct imaging gives us information we can't get any other way. We can study the planet's spectrum, analyzing what wavelengths of light it emits or reflects. This tells us about the atmospheric composition. We can measure the planet's temperature and how it varies across the surface. We can watch the planet over time, seeing how it changes as it orbits. In the future, as telescopes get larger and adaptive optics improves, we'll be able to image smaller, cooler, older planets. We'll image planets in wider orbits around more distant stars. The technique will become more powerful and reveal details we can only dream of today. The discovery raised immediate questions. How did something this massive form? How do you build a planet 9 times the mass of Jupiter? And, more importantly, how do you build it so far from its star where the protoplanetary disk would have been incredibly thin? To understand this, we need to talk about planet formation theory. There are 2 main models for how giant planets form. The first is called core accretion, and it's the standard model for how we think Jupiter and Saturn formed in our solar system. The second is called gravitational instability, and it might explain objects like ROX's 42BB. Core accretion starts with a protoplanetary disk, the rotating disk of gas and dust that surrounds a young star. The disk contains all the ingredients for planets: gas, mostly hydrogen and helium; dust, tiny solid particles made of rock, metal, and ice. In the inner disk, it's hot, so only rock and metal can exist as solids. In the outer disk, beyond the snow line, it's cold enough for water to freeze into ice. This is crucial because ice greatly increases the amount of solid material available. Planet formation begins when dust particles stick together through electrostatic forces and gentle collisions. Over time, these grow into larger clumps, then boulders, then mile-sized planetesimals. At this scale, gravity takes over. Planetesimals collide and merge, growing into protoplanets hundreds or thousands of miles across. In the outer solar system, if a protoplanet grows large enough, around 10 Earth masses, its gravity becomes strong enough to capture gas from the disk. And once this starts, it accelerates. The more gas the planet captures, the stronger its gravity gets, and the faster it can capture more gas. This is runaway gas accretion. Within a few 100,000 years, a planet can balloon from 10 Earth masses to hundreds of Earth masses. It becomes a gas giant, like Jupiter. This model works well for explaining Jupiter and Saturn. But it has problems explaining something like ROX's 42BB. At 157 astronomical units from the star, the protoplanetary disk would be extremely thin. There might not be enough material to build a 10 Earth mass core. Without that core, you can't trigger runaway gas accretion. The timescale is also a problem. Core accretion is slow, especially in the outer disk where collisions happen less frequently. At 157 astronomical units, it could take hundreds of millions of years to build a massive planet. But gas disks don't last that long. They typically disappear within 3 to 10 million years. This is where gravitational instability comes in. Instead of slowly building up from dust, the disk itself can become unstable. If a region becomes too dense, gravity overwhelms the pressure holding the disk in balance. The dense region collapses inward on itself, fragmenting into a clump that contracts under its own gravity. This clump becomes a planet or brown dwarf. The process is fast, just a few thousand years. And it can happen in the outer regions, where core accretion would be too slow. Gravitational instability requires specific conditions. The disk needs to be heavy, at least 10% of the star's mass. It needs to be cold, so gas pressure doesn't prevent collapse. These conditions are more likely in the outer parts of large, young disks. Exactly the kind of disk that would have surrounded Rox's 42B's star 2 million years ago. If Rox's 42B formed this way, it would have started as a diffuse clump of gas hundreds of times larger than it is now. Over time, it contracted, heating up as gravitational energy converted to thermal energy. It radiated away some of that heat, slowly cooling and shrinking. Eventually, it settled into something resembling a planet. But here's the interesting question. If it formed through gravitational instability, is it really a planet? Or is it more like a failed star? The formation process is identical to how binary stars form. A molecular cloud fragments into multiple pieces, each collapsing to form a star. If one piece doesn't get enough mass, it becomes a brown dwarf instead of a star. Rox's 42B might have formed exactly this way. The only difference is its mass ended up below the brown dwarf threshold. So, we call it a planet, by definition, even though it formed like a star. This is why the classifications get messy. What we do know is that Rox's 42B formed somehow, and the more planets we discover, the more we realize how diverse the process can be. Rox's 42B is just one example. There are other candidates for the title of biggest planet, and each one comes with its own complications. Consider HD 1000546b. This is one of the most controversial objects in exoplanet science. The planet, if we can call it that, orbits a young star about 335 light-years from Earth in the constellation Musca. Estimates of its mass vary wildly. Some studies suggest it could be as low as 6 Jupiter masses. Others suggest it might be as high as 20 Jupiter masses. 20 Jupiter masses would firmly place it in brown dwarf territory, not a planet at all. The uncertainty comes from the difficulty of observing it and the complexity of modeling what we see. What makes HD 1005446b particularly interesting is its location. It orbits extremely close to its star, at a distance of only about 53 astronomical units. For comparison, Neptune orbits our Sun at about 30 astronomical units. But this star is much younger and more active than our Sun. The protoplanetary disk is still present, still full of gas and dust. We might be watching a planet in the process of forming right now. Some observations suggest there's a gap in the disk at the location of HD 1000546b. This gap could be evidence that the planet is carving out a clear path as it sweeps up material from the disk. If the higher mass estimates are correct, and this object is closer to 20 Jupiter masses, it raises fascinating questions. Can something that massive still be forming? Or did it form elsewhere and migrate inward? The star system is only about 5 to 10 million years old. That's very young. Planet formation is still ongoing. We're seeing the system in a snapshot, frozen in time, long before it settles into a stable configuration. Other astronomers aren't even convinced HD 1005446b exists. Some of the observations could be explained by features in the disk itself, like spiral density waves or clumps of dust, rather than an actual planet. The debate continues. Every new observation either strengthens or weakens the case for its existence. This is how science works. We make observations, We propose explanations. We argue about the evidence. We make more observations, and gradually we converge on the truth. Now let's talk about size in a different way. Mass is one measure of how big a planet is. But diameter is another. Volume is yet another. And density ties them all together. When it comes to diameter, one of the record holders is TRES 4b. TRES 4b is what astronomers call a Puffy planet, and it's one of the strangest objects in our exoplanet catalogue. It has roughly the same mass as Jupiter, maybe a bit less, around 0.92 Jupiter masses. But its diameter is enormous, about 1.7 times larger than Jupiter. Let me put that in concrete numbers. Jupiter is about 86,881 miles, or about 139,820 kilometers in diameter. TRES 4b is about 148,600 miles, or about 239,000 kilometers across. That's a massive world. To visualize this, imagine Jupiter as a basketball. It's about 9.5 inches, or 24 centimeters in diameter. TRES 4b would be about 16 inches, or 41 centimeters in diameter, about the size of a large exercise ball. Now, here's the mind-bending part. The volume of a sphere increases with the cube of the radius. So, if TRES 4b has 1.7 times Jupiter's diameter, it has 1.7 cubed times Jupiter's volume. 1.7 cubed is about 4.9. So TRES 4b has roughly 5 times the volume of Jupiter. But it doesn't have 5 times the mass. In fact, it has slightly less mass than Jupiter. This means its density is extremely low. The average density is only about 0.2 grams per cubic centimeter. For comparison, Jupiter has a density of 1.33 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. Cork has a density of about 0.25 grams per cubic centimeter. TRES 4b has roughly the same density as cork. It's a planet the size of a large exercise ball with the density of cork. If you could somehow gather all the oceans on Earth into one place, TRES 4b would float. Not just float barely, but float high, with most of its volume above the water surface. Of course, this is a ridiculous thought experiment. You can't have an ocean big enough to float a planet in. And TRES 4b is a ball of gas thousands of degrees hot. But the density comparison helps illustrate just how puffy this planet is. So, why is it so puffy? The answer has everything to do with where it orbits and how hot it is. TRES 4b is what we call a hot Jupiter. These are gas giant planets that orbit extremely close to their stars. TRES 4b orbits its star at a distance of only about 0.05 astronomical units. That's 5% of the distance from Earth to the Sun. In more familiar units, that's about 4.7 million miles, or about 7.5 million kilometers. For perspective, Mercury, the closest planet to our Sun, orbits at 0.39 astronomical units. TRES 4b orbits more than 7 times closer than Mercury. At that distance, the star's radiation is intense. The planet receives about 400 times more energy per square meter than Earth receives from our Sun. The star in TRES 4b's sky would appear enormous, about 7 times larger in diameter than our Sun appears from Earth. The heat is crushing. The estimated temperature on the day side of TRES 4b is around 2,700 degrees Fahrenheit, or 1,482 degrees Celsius. That's hot enough to melt iron, which melts at 2,800 degrees Fahrenheit, or 1,538 degrees Celsius. At these temperatures, rock would glow red hot. Most metals would be liquid. Even some ceramics would soften. The night side is cooler, but not by much. Heat from the day side is transported around the planet by powerful winds. The temperature difference between day and night might only be a few hundred degrees. The entire planet is bathed in extreme heat. This heat causes the atmosphere to expand dramatically. When you heat a gas, the atoms and molecules move faster. They bounce off each other more energetically. They push outward with more force. The atmosphere wants to expand. On Earth, gravity is strong enough to hold the atmosphere in place despite its thermal energy. The atmosphere has a scale height, the distance over which pressure drops by a factor of E, of about 5 miles, or about 8 kilometers. This is why the atmosphere is thin. Most of the mass is concentrated near the surface. But on TRES 4b, two things are different. First, the temperature is much higher, so the thermal energy is much greater. Second, the gravity is relatively weak because the planet doesn't have much mass despite its large size. The combination means the atmosphere can expand to great distances. The scale height is probably hundreds or thousands of kilometers. The atmosphere is puffy, spread out over a huge volume. The gases aren't compressed into a dense layer. They form a tenuous, extended envelope around the planet. And here's what makes it even stranger. At 2,700 degrees Fahrenheit, many chemical compounds that normally exist as gases on cooler planets can't exist at all. Water breaks apart into hydrogen and oxygen. Methane breaks apart into carbon and hydrogen. Ammonia dissociates. Even molecular hydrogen, H2, starts to break apart into individual atoms at the highest temperatures. The atmosphere of TRES 4b is probably mostly atomic, hydrogen and helium, plus various ionized metals. Sodium, potassium, iron, magnesium, all vaporized by the heat and existing as individual atoms or ions in the gas. Spectroscopic observations have detected some of these elements. The planet's atmosphere absorbs light at specific wavelengths corresponding to sodium and other metals. This tells us what's present in the upper atmosphere. But we don't know the full composition yet. Detailed atmospheric modeling is difficult because these temperatures and pressures don't exist anywhere in our solar system. We can't test our models in laboratories. We have to rely on theoretical calculations and observations. TRES 4b was discovered in 2006 using the transit method. The planet passes in front of its star once every 3.55 days. During each transit, the planet blocks some of the star's light. The amount of dimming tells you how big the planet is relative to the star. For TRES 4b, the transit depth is large, about 1%. That means the planet blocks about 1% of the star's light when it passes in front. 1% might not sound like much, but it's huge for an exoplanet. Most planets block only a few tenths of a percent or less. Earth, transiting in front of our Sun, as seen from a distant star, would cause a dimming of only about 0.01%. The large transit depth for TRES 4b immediately told astronomers this was an unusually large planet. Follow-up observations with larger telescopes measured the planet's mass using the radial velocity method. As TRES 4b orbits, it pulls on its star. The star wobbles back and forth. From Earth, we see this as a Doppler shift in the star's spectral lines. By measuring the wobble amplitude and period, you can calculate the planet's mass. The measurements showed TRES 4b has slightly less mass than Jupiter. Combined with the large size from the transit observations, this gave the remarkably low density. Astronomers were puzzled. How can a planet be so puffy? The heat explains part of it. High temperatures cause atmospheres to expand, but most models predict that even a hot Jupiter should only be about 10 to 20% larger than Jupiter, not 70% larger. TRES 4b is far puffier than standard models predict. Several explanations have been proposed. One idea is that the planet has extra heating from the inside. Maybe tidal forces from the star are heating the interior. As the planet orbits, tidal bulges move around the planet. The friction from this movement could generate heat. This tidal heating could inflate the planet beyond what stellar radiation alone would cause. Another idea involves the planet's magnetic field. Hot Jupiters probably have strong magnetic fields generated by the motion of metallic hydrogen in their interiors. If the magnetic field interacts with charged particles in the atmosphere, it could deposit energy into the upper atmosphere. This could heat and inflate the atmosphere even more. A third possibility is that the planet's interior is unusually hot for some reason. Maybe it captured extra energy during formation. Maybe it has an unusual composition that affects how heat flows from the interior to the surface. We don't know for sure. All we know is that TRES 4b is significantly puffier than our models easily explain. It's pushing the boundaries of what we thought was possible for a gas giant planet. But here's the really interesting question. How long can TRES 4b stay this puffy? The intense radiation from the star doesn't just heat the planet. It can also strip away the atmosphere over time. High energy, ultraviolet, and X-ray radiation from the star can ionize atoms in the upper atmosphere. These ionized atoms can gain enough energy to escape the planet's gravity entirely. This process is called atmospheric escape, and it's a significant problem for hot Jupiters. Every second, TRES 4b is probably losing millions of kilograms of atmosphere to space. That sounds like a lot, and it is. But the planet is so massive that even losing millions of kilograms per second, it would take billions of years to lose a significant fraction of its mass. Still, over the planet's lifetime, atmospheric escape should cause it to shrink. The extended, puffy atmosphere should gradually erode away. Eventually, the planet should contract to something closer to Jupiter's size. And yet, here's TRES 4b, puffed up to 1.7 times Jupiter's diameter. Either the planet is young, and we're seeing it before it has had time to contract, or there's some mechanism constantly replenishing the atmosphere, replacing what's lost to escape. Or our models of atmospheric escape are wrong, and the loss rate is much slower than we think. This is one of the big mysteries in exoplanet science. We've found several puffy planets, and they all challenge our understanding. They're telling us something about planet atmospheres and heating mechanisms that we haven't figured out yet. TRES 4b orbits a star about 1,430 light-years from Earth. That's about 8.4 quadrillion miles, or about 13.5 quadrillion kilometers. The light we see from that system left during the 6th century, when the Byzantine Empire was at its height and before Islam had been founded. And yet, we can detect this planet. We can measure its size and mass. We can study its atmosphere. We can puzzle over why it's so puffy. From nearly 1,500 light-years away, we're learning about a world that would kill us instantly if we visited. A world where iron melts and hydrogen glows, and the atmosphere extends hundreds of thousands of miles into space. A world so strange, it seems impossible. And yet, it exists. It's out there right now, silently orbiting its star, slowly evaporating into space, a testament to the diversity of planets in our galaxy. Let's take a step back and think about what we mean when we talk about the biggest planet. Are we talking about mass? Are we talking about diameter? Are we talking about volume? Each measure gives you a different answer. Roxy's 42BB has one of the highest masses, 9 times Jupiter. TRES 4b has one of the largest diameters, 1.7 times Jupiter. There are other candidates depending on how you measure. HAT-P 32b, another hot Jupiter, has a diameter similar to TRES 4b. HAT-P 2b is another massive planet, possibly 11 Jupiter masses, though the exact value is uncertain. Kepler 7b is another puffy planet with a very low density. The list goes on. Each discovery adds to our catalogue of extreme worlds. But here's what's fascinating. The more we look, the more we find that planets come in amazing variety. There's no one-size-fits-all. Some are massive and small, compressed by their own gravity. Some are light and huge, puffed up by stellar radiation. Some orbit close to their stars, baking in intense heat. Some orbit far away in the cold darkness. Some have circular orbits. Some have wildly eccentric orbits that bring them close to their star and then fling them far away. Our solar system gave us 8 examples of planets. Now we've found thousands of exoplanets. And they're showing us that our solar system is not typical. In fact, it might be downright unusual. Let me tell you about the brown dwarf problem, because this is where things get really complicated. The 13 Jupiter mass limit is supposed to be a clear dividing line. Below that, you have a planet. Above that, you have a brown dwarf. But nature doesn't care about our definitions. There are objects right at that boundary, and we can't always measure their mass precisely enough to know which side they fall on. Take Roxy's 42BB again. 9 Jupiter masses. Clearly a planet, right? But what if the actual mass is a bit higher than we think? What if it's actually 11 or 12 Jupiter masses? The measurements aren't perfect. There's always some uncertainty. And then there's the question of how the object formed. If something forms in a protoplanetary disk, we call it a planet. If it forms from a collapsing gas cloud, we call it a brown dwarf or a star. But we can't always tell how an object formed just by looking at it. Imagine you have 2 objects, both with exactly 10 Jupiter masses. One formed in a disk around a star, building up from solid cores that accumulated gas. The other formed from a fragment of a molecular cloud, collapsing under its own gravity. Should we call them both planets? Should we call them both brown dwarfs? Or should we call one a planet and one a brown dwarf, based on their formation history, even though they're identical in mass and composition? There's no consensus answer. Different astronomers have different opinions. Some argue that mass is all that matters. below 13 Jupiter masses, it's a planet, no matter how it formed. Others argue that formation history matters. If it formed like a star, it's a brown dwarf, even if it's less massive than 13 Jupiter masses. The International Astronomical Union, the organization that officially defines astronomical terms, has tried to clarify this. They suggest that objects below 13 Jupiter masses that orbit stars should be called planets, regardless of how they formed. Objects above 13 Jupiter masses are brown dwarfs. And objects that don't orbit stars are sub-brown dwarfs if they're below 13 Jupiter masses, or brown dwarfs if they're above. But even this definition has problems. What about objects that used to orbit a star but were ejected? Are they still planets? Or do they become sub-brown dwarfs the moment they're kicked out of their system? What about objects in binary systems where both objects are planetary mass? Are they both planets, or is one a planet and one a moon? These might seem like pointless semantic debates. Who cares what we call them? But the definitions matter because they shape how we think about these objects and how we study them. If we classify something as a planet, we think about it in terms of planet formation theories. If we classify it as a brown dwarf, we think about it in terms of star formation theories. The classification guides our research. The reason we can find these planets at all is because of major advances in detection technology over the past few decades. The first exoplanet around a sun-like star was discovered in 1995 using the radial velocity method. As a planet orbits, both the planet and star orbit their common center of mass. This causes the star to wobble. From Earth, we see this wobble as a Doppler shift in the star's light. By measuring these tiny shifts, we can detect the planet, measure its mass, and determine its orbital period. The radial velocity method works best for large planets close to their stars because they cause bigger, faster wobbles. This is why so many early discoveries were hot Jupiters. The transit method came next. When a planet passes in front of its star, as seen from Earth, the star dims slightly. The amount of dimming tells you the planet's size. The timing tells you the orbital period. The Kepler Space Telescope, launched in 2009, used this method to find thousands of exoplanets. It stared at 150,000 stars and watched for transits. We now know that nearly every star has at least one planet. There are more planets in our galaxy than there are stars. But both methods have limitations. They favor finding planets close to their stars. A planet at 157 astronomical units, like Rox's 42BB, takes 2,000 years to orbit. You'd have to watch for 2,000 years to see one complete transit. This is where direct imaging comes in. With direct imaging, you actually photograph the planet itself. Stars are vastly brighter than planets, but it's possible under certain conditions. If the planet is far from its star, hot enough to glow in infrared, and the star is young and relatively faint, direct imaging becomes feasible. Rox's 42BB has all these advantages. Each method has its strengths. Together, they give us a comprehensive picture of the exoplanet population, and new techniques are constantly being developed. Now, let's talk about what these massive planets tell us about how planetary systems form and evolve. Because finding planets like Rox's 42b and Tres 4b isn't just about cataloging weird worlds. It's about understanding the fundamental processes that create planetary systems. Every discovery gives us data to test our theories. Every strange planet forces us to expand our models. And massive planets, in particular, are crucial because they have outsized effects on their planetary systems. The traditional model of planet formation that I described earlier, core accretion in a protoplanetary disk, works well for our solar system. But it was developed based only on our solar system. We had a sample size of 8 planets, 1 star, 1 system. That's not a lot of data to build a universal theory from. For decades, astronomers assumed our solar system was typical, that most systems would look similar. Small, rocky planets close to the star, gas giants farther out, everything in nearly circular orbits, all orbiting in the same plane. Then, in 1995, we discovered 51 Pegasi b, a gas giant orbiting its star every 4 days. This was shocking. A gas giant can't form that close to a star. It's too hot for ices to condense. There's not enough solid material to build a massive core. The planet must have formed farther out and then migrated inward. But how? This question led to the development of planetary migration theory. There are several mechanisms by which planets can move from their formation locations. The first is disk migration. When a planet orbits through a gas disk, it creates spiral density waves in the gas, like the wake behind a boat. These waves carry angular momentum. If the waves inside the planet's orbit are stronger, they push the planet outward. If the waves outside are stronger, they pull the planet inward. For most configurations, the net effect is inward migration. The planet spirals toward the star. For small planets, this migration is slow. The planet might move only a small fraction of an astronomical unit over the disk's lifetime. But for massive planets, migration can be fast. A Jupiter-mass planet can migrate from 5 astronomical units to 0.1 astronomical units in less than 1 million years. That's incredibly fast on cosmic timescales. This Type 2 migration, as it's called, happens when the planet is massive enough to open a gap in the disk. The planet sweeps its orbital zone clear of gas, creating an empty lane. But gas, from inner and outer parts of the disk, flows across this gap. As it does, it pushes on the planet, causing it to migrate. The migration continues as long as there's gas in the disk. Once the disk dissipates, migration stops. The planet is frozen, in whatever orbit it happens to be in, when the gas disappears. This explains hot Jupiters, like TRES 4b. They formed in the outer disk, where there was enough solid material to build a core. Then, they migrated inward, through the gas disk. They ended up very close to their stars, because they migrated quickly, and the gas disk lasted long enough for them to get there. But disk migration isn't the only mechanism. There's also planet-planet scattering. If a system forms multiple massive planets, they can gravitationally interact with each other. If 2 planets come too close, they can scatter each other into new orbits. One planet might get kicked outward, gaining energy and moving to a wider orbit. The other planet loses energy and drops into a tighter orbit. In extreme cases, one planet can be ejected from the system entirely, becoming a free-floating planet drifting through interstellar space. Computer simulations show that planet-planet scattering can produce planets in very eccentric orbits. Instead of near circular orbits like the planets in our solar system, scattered planets can have highly elliptical orbits. They swing in close to the star at one point in their orbit, then swing far out at another point. These eccentric orbits can later be circularized by tidal forces from the star. As the planet swings close to the star, tidal bulges form. These bulges are pulled on by the star's gravity, which removes energy from the planet's orbit. Over millions of years, the orbit becomes more and more circular. Eventually, you end up with a hot Jupiter in a circular orbit. But it got there through a completely different process than disk migration. Yet another mechanism is the Kozai-Lidov mechanism. This happens in systems where there's a third body, like a second star or a distant massive planet orbiting the inner system. The gravitational influence of this third body can cause the inner planet's orbit to oscillate. The eccentricity increases, causing the orbit to become more and more elliptical. At the same time, the orbital inclination changes. The planet's orbit tilts relative to the rest of the system. When the eccentricity is high and the planet swings close to the star, tidal forces can again circularize the orbit. The end result is a planet in a circular orbit close to its star, but potentially with an orbit tilted relative to the star's equator. We've observed hot Jupiters with misaligned orbits, orbiting at steep angles or even retrograde, going the opposite direction of the star's rotation. These misaligned hot Jupiters are evidence for high eccentricity migration driven by the Kozai-Lidov mechanism. All of these mechanisms, disk migration, planet-planet scattering, and Kozai-Lidov migration, probably happen in nature. Different systems probably form through different pathways. Some hot Jupiters migrated through gas disks. Some were scattered and then circularized. Some underwent high eccentricity migration. And we're learning to distinguish between these scenarios by studying the orbits and system architectures. Systems with multiple planets in regular orbits probably didn't experience much scattering. Systems with misaligned hot Jupiters probably underwent high eccentricity migration. Systems with planets in mean motion resonances, where orbital periods are simple ratios, probably migrated together through a disk. Every detail matters. Every measurement of an orbit, a mass, a radius, an atmospheric composition adds to our understanding. Massive planets are particularly important because they're the ones that drive these dynamics. A planet like Rox's 42b, if it has siblings, could scatter them into wild orbits. Its massive gravity would dominate the system's evolution. Or, if it formed in place through gravitational instability, it tells us that massive planets can form far from their stars without migrating. This has implications for how common different types of planetary systems are. If massive planets can only form close to stars and then migrate outward, we'd expect certain patterns. If they can form far from stars through direct collapse, we'd expect different patterns. By finding planets like Rox's 42b and studying where they are and how they orbit, we're testing these theories. We're learning which formation pathways are common and which are rare. We're understanding the full range of possibilities. Another thing massive planets teach us about is the metallicity connection. Metallicity, in astronomy, doesn't mean metals like iron and copper. It means any element heavier than hydrogen and helium. Carbon, oxygen, silicon, iron, all of these are metals in astronomical terms. Observations have shown that stars with higher metallicity are more likely to host giant planets. This makes sense in the context of core accretion. If a protoplanetary disk has more heavy elements, there's more solid material to build cores. Larger cores form faster and are more likely to reach the critical mass needed to trigger runaway gas accretion. So high metallicity stars should produce more gas giants. And that's exactly what we observe. Stars with twice the solar metallicity are about 3 times more likely to have a giant planet than stars with solar metallicity. Stars with half the solar metallicity are much less likely to host giants. But the correlation isn't perfect. We've found giant planets around metal-poor stars. We've found stars with high metallicity that don't have giants. The metallicity just changes the odds. It doesn't guarantee anything. And for the most massive planets, the ones near the planet brown dwarf boundary, the metallicity connection is less clear. These objects might form through gravitational instability, which is less dependent on metallicity. A massive disk can fragment regardless of its heavy element content. So studying objects like Rox's 42Bb might reveal a different formation channel that doesn't depend on metallicity the way core accretion does. We're also learning about planetary system stability. Not all planetary systems are stable over long timescales, and not all planetary systems, if planets are too close together, their gravitational interactions can destabilize the system. Over millions or billions of years, the orbits can become chaotic. Planets might collide. Planets might be ejected. The system can self-destruct. Computer simulations can model this. You set up a system with certain planets in certain orbits. You run the simulation forward in time, calculating the gravitational forces at each step. You see what happens. Some configurations are stable for billions of years. Others fall apart in just a few million years. By studying real planetary systems and seeing which configurations actually exist, we learn which setups are stable. We can rule out certain arrangements because they wouldn't survive. Massive planets have a big impact on system stability. A massive planet can keep smaller planets in stable orbits through its gravitational influence. Or it can kick them out of the system entirely if the geometry is wrong. Systems with multiple massive planets are particularly interesting. The planets have to be spaced far enough apart that they don't perturb each other too much. If they're too close, the system becomes unstable. There's a rough rule. Planets need to be separated by at least about 10 mutual Hill radii to remain stable. The Hill radius is the distance from a planet within which the planet's gravity dominates over the star's gravity. For Jupiter, the Hill radius is about 0.35 astronomical units. So multiple Jupiters would need to be separated by at least 3 to 4 astronomical units to coexist stably. Our solar system satisfies this. Jupiter and Saturn are separated by about 4.3 astronomical units. They're stable. But we've found systems where multiple giants are packed more tightly. These systems must have formed differently or be in temporarily stable configurations that will eventually break down. Studying these systems helps us understand orbital dynamics and long-term evolution. It's like having natural experiments in celestial mechanics playing out across the galaxy. We observe the results and work backward to understand the physics. The massive planets, like Rox's 42Bb and HD 100546b, present their own challenges. If they formed in a disk, how did they accumulate so much mass? Disks have finite amounts of material. Building something 9 times Jupiter's mass requires sweeping up material from a huge area. And at 157 astronomical units, where Rox's 42BB orbits, the disk is so thin that there might not be enough material. This is why some astronomers think these objects formed through gravitational instability. If a region of the disk becomes dense enough, it can collapse directly into a massive clump without going through the slow process of core accretion. This can happen in the outer parts of large disks around young stars. The clump contracts, heats up, and becomes a planet or brown dwarf. This process is faster than core accretion and can produce very massive objects. But it requires special conditions. The disk needs to be massive and cold. Most disks don't meet these requirements. We're still working out the details. Every new discovery gives us more data to test our theories. And the more we learn, the more we realize how diverse planet formation can be. There's no single story. There are many pathways, many outcomes, many possibilities. Let's talk about what the future holds for finding even bigger planets. The James Webb Space Telescope, launched in December of 2021, is revolutionizing exoplanet science. And we're only seeing the beginning of what it can do. Webb is different from previous space telescopes in fundamental ways. The Hubble Space Telescope, launched in 1990, was designed primarily for visible and ultraviolet light. Webb is optimized for infrared observations. Its mirror is 6.5 meters or 21 feet across, much larger than Hubble's 2.4-meter or 8-foot mirror. Larger mirrors collect more light and provide better resolution. But the real advantage is infrared sensitivity. Infrared light penetrates dust that blocks visible light. It can see cooler objects that don't emit much visible light. And it's perfect for studying exoplanets. Planets are cool compared to stars. They emit most of their radiation in the infrared. Young, massive planets like Rox's 42b are especially bright in the infrared because they're still hot from formation. Webb can detect this thermal emission directly. It can take spectra of planetary atmospheres, breaking the light into its component wavelengths. Different molecules absorb and emit at different wavelengths, creating a unique fingerprint. By analyzing these fingerprints, we can determine what a planet's atmosphere is made of. Water vapor, carbon dioxide, methane, ammonia, sodium, potassium, even complex organic molecules. Webb has already made stunning discoveries in its first couple years of operation. It's detected water vapor, carbon dioxide, and methane in the atmosphere of WASP 96b, a hot Jupiter. It's imaged the debris disk around the star Fomalhaut with stunning detail, showing multiple rings and gaps that might indicate unseen planets. It studied the atmosphere of the super-Earth K 218b and found potential signs of carbon-bearing molecules. For massive planets like Rox's 42b, Webb's capabilities are transformative. It can take direct images of these planets with much better sensitivity than ground-based telescopes. It can characterize their atmospheres in detail. It can detect fainter, cooler, older planets that previous telescopes couldn't see. And it can study planets in the process of forming, observing protoplanetary disks and spotting the signatures of embedded planets. One of Webb's key instruments is the near-infrared camera, or NIRCam. This camera operates at wavelengths from 0.6 to 5 microns in the near-infrared. It can image planets directly, using coronagraphs to block starlight. It has the sensitivity to detect planets much fainter than anything we could see before. Another crucial instrument is the mid-infrared instrument, or MIRI. MIRI operates at longer wavelengths, 5 to 28 microns. At these wavelengths, planets emit much more relative to their stars than at shorter wavelengths. The brightness contrast is more favorable. MIRI can also take spectra, measuring the atmospheric composition. Webb's near-infrared spectrograph, NIRSpec, can observe multiple objects simultaneously. It can study a planet's spectrum over a wide range of wavelengths in a single observation. This allows detailed atmospheric characterization. But Webb is just the beginning. Ground-based telescopes are getting larger and more advanced. The Extremely Large Telescope, or ELT, is currently under construction in Chile. It's being built by the European Southern Observatory and should see first light in the late 2020s. The name is appropriate. The primary mirror will be 39 meters, or 128 feet in diameter. That's almost 4 times larger than any existing optical telescope. To put that in perspective, if you laid the mirror on a football field, it would stretch from one end zone to nearly the 30-yard line. The mirror is so large, it has to be built from 798 hexagonal segments, each 1.4 meters, or about 4.6 feet, across. These segments have to be aligned to within nanometers of precision. Computer-controlled actuators continuously adjust each segment to maintain perfect alignment. With adaptive optics, the ELT will achieve resolution about 15 times better than Hubble. It will be able to image exoplanets directly with unprecedented clarity. For massive planets like Roxy's 42Bb, the ELT could resolve details on the surface. It might detect weather patterns, storm systems, variations across the day-night boundary. It could take spectra at different locations on the planet, mapping the atmospheric composition across the globe. And it will be able to image much fainter planets. Cooler planets, older planets, planets that aren't as massive or hot. The ELT will push the boundaries of what's possible with ground-based astronomy. The Giant Magellan Telescope, or GMT, is another next-generation facility under construction in Chile. Its design is different from the ELT. Instead of hundreds of small segments, it uses 7 8.4-meter or 27.6-foot mirrors arranged in a hexagonal pattern. 6 outer mirrors surround one central mirror. Together, they have the light-collecting area of a 24.5-meter or 80-foot telescope. The GMT is optimized for high-resolution spectroscopy and imaging. It will have adaptive optics systems that can compensate for atmospheric turbulence across a wide field of view. For exoplanet science, the GMT will excel at detailed spectroscopic studies. It can take extremely high-resolution spectra of planetary atmospheres. It can measure wind speeds from Doppler shifts. It can detect individual molecular absorption lines. The 30-meter telescope, or TMT, is planned for Mauna Kea in Hawaii, though the project has faced delays and controversies. As the name suggests, it will have a 30-meter or 98-foot diameter mirror made of 492 segments. The TMT will have capabilities similar to the ELT and GMT. Together, these 3 extremely large telescopes will form a powerful network spanning the globe. They'll be able to observe different parts of the sky, track objects continuously as Earth rotates, and cross-check each other's findings. But ground-based telescopes, no matter how large, still have to deal with Earth's atmosphere. Adaptive optics helps, but it's not perfect. This is why space-based missions remain crucial. The Nancy Grace Roman Space Telescope, formerly known as WFIRST, is scheduled to launch in the late 2020s. It's a NASA mission with a primary mirror 2.4 meters or 8 feet across, the same size as Hubble's. But it has a much wider field of view. It can observe areas of sky 100 times larger than Hubble in a single image. For exoplanet science, Roman will use two main techniques. Gravitational microlensing can detect planets at any distance from their stars, from close in to far out. It can even detect free-floating planets that don't orbit any star at all. Roman will conduct a massive microlensing survey toward the galactic center, where stars are densely packed. This survey is expected to find thousands of new planets. It will give us statistical information about how common different types of planets are. It will tell us whether planets like Earth are rare or common. It will detect planets we could never find any other way. Roman will also do direct imaging using a coronagraph. The coronagraph is designed to achieve extraordinary contrast ratios, blocking starlight by a factor of 1 billion or more. This will allow it to image Jupiter like planets in Earth, like orbits around nearby stars. Something that's extremely difficult with current technology. The European Space Agency's Plato mission, scheduled to launch in 2026, will search for Earth like planets around nearby stars. Plato stands for planetary transits and oscillations of stars. It will use the transit method, monitoring hundreds of thousands of stars continuously for years. The long observation baseline will allow it to detect planets in longer period orbits. Planets that take a year or more to orbit their stars. These are the planets we've had trouble finding so far, because you need multiple transits to confirm a detection. Plato will watch stars long enough to see multiple transits, even for planets with year-long orbital periods. It will focus on bright nearby stars where follow-up characterization is feasible. Looking even further ahead, the Habitable Worlds Observatory is still in early planning stages. It's envisioned as a large space telescope specifically designed to find and characterize potentially habitable planets. The mission would use a starshade, a huge flower-shaped screen that flies in formation with the telescope. The starshade blocks the star's light before it even enters the telescope. This allows much better contrast than a coronagraph alone. The combination could image Earth-sized planets in the habitable zones of nearby Sun-like stars. It could take spectra of their atmospheres, searching for biosignature gases, oxygen, ozone, methane, water vapor, the combinations that might indicate life. This is the holy grail of exoplanet science. Finding another Earth, proving we're not alone. For massive planets, all these future missions and telescopes will find more examples. Bigger, stranger, more extreme than anything we've found so far. We'll image planets with 10, 12, 15 Jupiter masses. We'll study their atmospheres in detail. We'll watch them cool and evolve over time. We'll map their temperature structures, wind patterns, cloud formations. We'll detect their magnetic fields through radio emissions. We'll find planets around binary stars, planets in stellar clusters, planets in the galactic halo. Every new capability opens new parameter space. Every new instrument reveals things we couldn't see before. The pace of discovery is accelerating. In 20 years, our catalogue of exoplanets will be vastly larger and more detailed than it is today. We'll have characterized hundreds of massive planets. We'll understand formation mechanisms much better. We'll know which types of planets are common and which are rare. We'll have a complete census of our galactic neighborhood. And somewhere in all that data, we might find something truly unexpected. A planet so massive or so strange that it breaks all our models. An object that forces us to completely rethink what's possible. That's what makes this so exciting. We're exploring uncharted territory. Every observation could be the one that changes everything. Let's think about what it means that we can find these massive worlds from Earth. 460 light-years away, Rox's 42b orbits its young star. The light we're seeing from that system left when Galileo was using his first telescopes to observe Jupiter's moons. That light traveled through space for 460 years. It crossed the vast emptiness between stars. It passed through interstellar gas and dust. And it arrived at Earth, where we captured it with our telescopes and used it to detect a planet. We measured that planet's mass, size, temperature, and orbit. We determined that it's 9 times more massive than Jupiter. We figured out how hot it is. We're studying its atmosphere, trying to understand what it's made of and how it formed. All of this from light that traveled for 4 centuries. This is one of humanity's greatest achievements. We're tiny creatures on a small planet. We live for mere decades. Our entire species has only been around for a few 100,000 years. And yet, we've figured out how to detect planets around other stars. We've built the mathematics and technology to understand objects we can never visit. We've revealed that the universe is filled with worlds beyond imagination. Think about what this required. Centuries of scientific progress, Newton's laws of motion and gravity, the development of spectroscopy to analyze light, Einstein's theory of relativity to understand how gravity affects light, quantum mechanics to understand atoms and molecules, the invention of telescopes, cameras, computers, and space missions. Thousands of scientists and engineers working together across generations, all building on each other's work, adding to humanity's collective knowledge. The discovery of Rox's 42b didn't happen in a vacuum. It was the result of all this accumulated knowledge and technology. And it's not just about finding big planets. It's about understanding our place in the universe. For most of human history, Earth was all we knew. The idea that other planets existed around other stars was pure speculation. Maybe they existed, maybe they didn't. We had no way to know. Now we know. Planets are everywhere. They come in types we never imagined. Some are larger than anything in our solar system. Some are smaller. Some are hot, some are cold. Some orbit close to their stars. Some orbit far away. Some are alone. Some are in systems with multiple planets. The diversity is remarkable. And it tells us that the universe is far more interesting and varied than we ever expected. It also tells us that our solar system is just one example among billions. We're not special in that sense. We're one planetary system among countless others. But we are special in another way. We're the ones asking the questions. We're the ones building the telescopes and doing the math. We're the ones trying to understand it all. As far as we know, We're the only species in the universe that can do this. That makes us remarkable. Let me tell you something that might surprise you. Despite all we've learned, despite thousands of exoplanet discoveries, we still don't know what the absolute biggest planet possible is. We know there's a theoretical limit. At 13 Jupiter masses, you cross into brown dwarf territory and deuterium fusion begins. But the exact maximum size a planet can have before fusion starts depends on its composition and internal structure. A planet made of pure hydrogen will reach that limit at a lower mass than a planet with heavier elements mixed in. Temperature matters too. A hotter planet will be more expanded, while a cooler one will be more compressed. Age matters. Young planets are still contracting and cooling from their formation. Old planets have settled into their final size. There might be planets right at the edge, 12 or 13 Jupiter masses, that we haven't found yet. There might be even more massive objects that don't quite fuse deuterium because of their composition. Every discovery teaches us something new. Every massive planet we find helps us refine our models. And there's another possibility we haven't talked about much. Free-floating planets. These are planets that don't orbit any star. They were either ejected from their planetary systems through gravitational interactions, or they formed alone in interstellar space. We've found several free-floating planetary mass objects. Some of them are quite massive, 10 or more Jupiter masses. Without a star to orbit, these objects are incredibly difficult to find. We can only detect them if they pass in front of a background star, causing a gravitational microlensing event. Or if they're young and hot enough to emit detectable infrared radiation. There could be billions of these rogue planets drifting through the galaxy. Some could be absolutely massive, right at the planet-brown dwarf boundary. We simply don't know because we can't see most of them. They're out there, in the darkness between the stars, invisible and unreachable with current technology. The galaxy might be full of giant worlds we'll never see. Let's zoom out even further and think about what massive planets mean for the possibility of life. Could a planet like Rox's 42BB have life? Almost certainly not. It's a gas giant with no solid surface. The temperature is thousands of degrees. Any organic molecules would be torn apart. The radiation environment would sterilize anything trying to survive. But could such a planet have moons that support life? That's more interesting. In our solar system, some of the most promising places to look for life are moons. Europa, orbiting Jupiter, has a subsurface ocean of liquid water. Enceladus, orbiting Saturn, has geysers of water shooting into space. Titan, also orbiting Saturn, has lakes and rivers of liquid methane on its surface. These moons are warmed by tidal heating. As they orbit their giant planets, the gravity causes them to flex and stretch, generating internal heat. This heat can maintain liquid water beneath ice shells or create complex chemistry in hydrocarbon lakes. A planet 9 times the mass of Jupiter would have enormous gravity. Any moons orbiting it would experience intense tidal forces. If those moons were in the right location and had the right composition, tidal heating could create habitable environments. Of course, there's a problem. Rox's 42b orbits 157 astronomical units from its star. At that distance, the star provides almost no heat or light. The moons would be frozen worlds in permanent darkness. Tidal heating alone probably wouldn't be enough to create surface oceans. But what about a massive planet in a different location? A planet several times Jupiter's mass orbiting in the habitable zone of its star, where temperatures are right for liquid water. Such a planet could have large moons. Those moons could be warmed by both the star and tidal heating. They could have atmospheres, oceans, possibly even life. We haven't found many massive planets in habitable zones yet, but they could exist. The search for exomoons, moons orbiting exoplanets, is just beginning. It's incredibly difficult because moons are so small compared to planets. But if we find them, and if some of them are in habitable zones around giant planets, they become prime targets in the search for life. Imagine a moon the size of Earth, orbiting a planet 5 times Jupiter's mass. The moon has oceans and continents. But in its sky, instead of a moon, there's a giant planet filling half the sky. Storms rage across the planet's surface, bands of clouds swirling in complex patterns. The moon's day-night cycle is complicated by eclipses as it passes through the planet's shadow. Auroras dance in the sky, far more spectacular than Earth's, powered by the planet's massive magnetic field. This is science fiction today, but it might be science fact tomorrow. We're finding planets stranger than anything we imagined. Why not moons equally strange and wonderful? Here's something that keeps astronomers up at night. The planets we've found so far are biased towards certain types. We find lots of hot Jupiters because they're easy to detect. We find lots of planets around small dim stars because the planets have a bigger effect on those stars. We find fewer planets around Sun, like stars at Earth, like distances, because the signals are so subtle. This means our current catalogue of exoplanets doesn't represent the true population. It's like conducting a survey of ocean life by only looking at the surface. You'd find lots of jellyfish and seabirds, and you'd conclude the ocean is mostly jellyfish and seabirds. But you'd miss the whales, the fish, the coral reefs, everything in the deep. The same is true for exoplanets. We're starting to scratch the surface, but there's so much we're still missing. There could be planets far more massive than Rox's 42Bb that we haven't detected because they're too cold or too far from their stars, or around stars too distant. There could be entire classes of planets we haven't imagined. Objects that don't fit our categories. Worlds so strange, they challenge our definitions. This is the frontier. This is what makes exoplanet science so exciting. Every observation could reveal something completely unexpected. And as our technology improves, we'll find more. Smaller planets, cooler planets, planets around faint stars, planets in systems unlike anything we know. Each discovery will teach us something new about how planets form, how they evolve, what's possible in the universe. Let me bring this back to something personal. You're a human living on Earth in the 21st century. You exist at a unique moment in history. For the first time ever, our species knows that planets orbit other stars. We can study them, categorize them, understand them. Your ancestors looked up at the same stars and wondered if other worlds existed. They could only speculate. You don't have to speculate. You know. There are thousands of confirmed planets, probably billions, in our galaxy alone. Some are small and rocky like Earth. Some are massive gas giants that dwarf Jupiter. Some are so strange they seem impossible. And you're alive to witness the discoveries. You can watch as new planets are announced. You can see the images, read the papers, follow the science. This knowledge is available to you in a way it never was to anyone who came before. Think about what that means. Galileo would have given anything to know what you know. He spent his life observing the sky with primitive telescopes, discovering moons around Jupiter, observing the phases of Venus. He was persecuted for suggesting Earth wasn't the center of the universe. He died under house arrest. But he would be amazed by what you know. Thousands of planets around other stars. Worlds larger than anything he could imagine. Isaac Newton spent decades working out the mathematics of gravity and planetary motion. His work was revolutionary, transforming our understanding of the universe. But he only knew the planets of our solar system. He would be stunned to learn about hot Jupiters, about planets orbiting so close to their stars they complete an orbit in hours. He'd want to apply his mathematics to these new worlds, to understand their orbits and predict their motions. Every scientist who came before would be envious of what you have access to. And it's not just scientists. This knowledge belongs to everyone. It's part of human culture now. We live in a universe filled with planets. That's not speculation anymore. That's fact. And it changes how we see ourselves. We're not alone in the cosmic sense. Even if we never find life elsewhere, we know the universe is full of worlds. Places where physics and chemistry create structures, environments, systems. The universe is not empty. It's populated with countless planets, each one unique. Let's end with this thought. The biggest planet we've ever discovered is massive beyond comprehension. 9 times the mass of Jupiter, 2,862 times the mass of Earth, 157 astronomical units from its star, in an orbit that takes 2,000 years to complete, hot enough to glow in the infrared, radiating away the energy from its formation, young enough that it's still contracting, still settling into its final form. And somewhere out there, in a distant solar system, 460 light-years away, it orbits. Right now, at this very moment, it's completing another tiny fraction of its 2,000-year orbit. It will complete its next orbit around the year 4000. Storms rage in its atmosphere, powered by internal heat. Winds howl at speeds we can barely imagine. Heat radiates from its interior, escaping to space. Gravity warps space-time around it, bending the fabric of reality itself. And we can see it. We can measure it. We can study it. From 93 million miles away, sitting on our small planet, we pointed our telescopes at that distant star and found its massive companion. We analyzed the light. We calculated the mass. We determined the temperature. We figured out how it formed and how it will evolve. That's extraordinary. That's the power of human curiosity and ingenuity. That's what we can accomplish when we build on centuries of accumulated knowledge. When we combine observations with mathematics. When we test our theories against reality. When we refuse to accept ignorance as an answer. We built the tools. Telescopes with mirrors larger than houses. Adaptive optics systems that adjust thousands of times per second. Spectrographs sensitive enough to detect the wobble of a star caused by a distant planet. Coronagraphs that can block out a star's light to reveal the faint glow of an orbiting world. We developed the theories, Newton's laws of motion and gravity. Einstein's general relativity, quantum mechanics to understand atomic spectra, computational fluid dynamics to model planetary atmospheres. We made the observations. Thousands of hours of telescope time, years of patient work, multiple observations to confirm and verify, peer review to ensure accuracy. We discovered worlds beyond our solar system, and we're just getting started. The next generation of telescopes will find planets we can't see today. They'll reveal details we can only guess at now. They'll answer questions we haven't thought to ask yet. Maybe they'll find something even more massive than Roxy's 42b, a planet of 12 Jupiter masses right at the edge of the brown dwarf boundary. Or 13 Jupiter masses, technically a brown dwarf, but barely distinguishable from a planet. Maybe they'll find moons orbiting these giant planets, worlds the size of Earth, warmed by tidal forces, potentially habitable. Maybe they'll find something completely unexpected that forces us to rethink everything. An object that doesn't fit our categories. A planet with properties we thought impossible. Something so strange it rewrites the textbooks. That's the beauty of exploration. You never know what you'll find. The universe is under no obligation to make sense to us. It doesn't care about our categories and definitions. It doesn't conform to our expectations. It just is, in all its complexity and strangeness. And we get to figure it out, piece by piece, discovery by discovery, one observation at a time, one calculation at a time, one insight at a time, building a picture of reality that gets clearer and more complete with each passing year. We've learned that planets orbit other stars. We've learned that these planets come in remarkable variety. Some small, some large, some absolutely massive. Some rocky, some gaseous, some we can't even classify. Some close to their stars, some far away, some in between. Some in circular orbits, some in eccentric orbits, some in misaligned orbits. We've learned that planet formation is more diverse than we imagined. That migration is common. That dynamical interactions reshape systems. That what we see today isn't necessarily what formed billions of years ago. We've learned to measure the unmeasurable, to see the invisible, to understand the incomprehensible. And with each discovery, we gain perspective. We see our place in the cosmic context. We're on one planet among billions. Our star is one among hundreds of billions. Our galaxy is one among trillions. The scale is humbling. But it's also inspiring, because despite our smallness, we can understand. We can look out at the universe and comprehend what we're seeing. We can measure distances of light years. We can calculate masses of planets we'll never visit. We can determine temperatures of atmospheres trillions of miles away. We can trace the history of planetary systems back to their formation billions of years ago. That's remarkable. That's what makes us special. Not that we're at the center of the universe. We're not. Not that we're important on a cosmic scale. We're not. But that we're conscious. We're aware. We can think and reason and discover. We can ask questions about the universe and figure out the answers. That's extraordinary, even if it's happening on a tiny planet in an unremarkable corner of an ordinary galaxy. So the next time you look up at the night sky, remember what's out there. Not just stars, but planets. Thousands of them that we know about. billions more that we haven't found yet. Some small, some large, some absolutely massive. Worlds orbiting other suns. Places we'll probably never visit, but places we can understand. Places that tell us about how planets form and evolve. Places that expand our conception of what's possible. And remember that every point of light you see is a sun. And around many of those suns, planets orbit. Gas giants, larger than Jupiter. Rocky worlds, smaller than Earth. Ice giants, hot Jupiters, super-Earths, mini-Neptunes. A diversity of worlds we're only beginning to catalogue and comprehend. Some of those planets might have life. We don't know yet. But we're looking. We're building better telescopes. We're developing better techniques. We're searching for biosignatures in planetary atmospheres. We're trying to answer one of humanity's oldest questions. Are we alone? And even if we don't find life, even if we discover that Earth is unique, we're still learning remarkable things. We're mapping the galaxy. We're understanding planetary systems. We're revealing the universe in all its glory. Thank you for joining me on this journey to the biggest planets in the universe. If you found this exploration fascinating, a like or subscribe would mean a lot. It helps this channel keep exploring the mysteries of space. And remember, every time you look up, you're looking at a universe far stranger and more wonderful than we ever imagined. A universe filled with worlds beyond counting. A universe where planets 9 times the mass of Jupiter exist in 2,000-year orbits. A universe where gas giants puff up to impossible sizes under the heat of their stars. A universe where brown dwarfs blur the line between planet and star. A universe of complexity and beauty and mystery. A universe we're privileged to explore, one discovery at a time. Good night, and keep looking up.